So I'm going to give you all a presentation or an introduction to type theory. It's another foundation of mathematics than the one most of you are used to, and it's closely related with the previous talk. First, I'm going to give a little bit of history how this foundation of type theory has come into play, and also some motivation why one actually wants to use another foundation, the one we're used to. Why one could consider it, and getting that one should. But okay, so I think modern mathematics it all started in around 1874, where Cantor actually for the first time formalized something like set theory, but soon after it turned out that actually it was not a good theory after all, because there were some paradoxes. This was one which Russell found, and so Russell put his mind to actually finding something which would work. And this actually started in a couple of papers between 1902 and 1908, where he gave something like a theory of types. It's not yet type theory as we know it. It actually still uses somewhat of this set theory, but I think this was the starting point of type theory. But actually, a long time after this, it has not been used, or at least definitely not in mathematics. Type theory really started having this important when Per Martin Loff introduces his notion of type theory. This is also called intuitionistic type theory or dependent type theory. So this is the one which we're going to discuss a little bit about, and then also an extension called Homotopy type theory. Okay, so yes, we want to use type theory instead of set theory or even category theory. Well, to give some simple reasons. The first is set theory and category theory. They're both not foundations on its own. They both use logic, so it's not that set theory is stands on its own, and so it's actually not a proper foundation, so to say. And also, set theory is actually very complicated. Although we actually use it, we never use it really how it is formalized. Because, for example, just the natural numbers, like the number 2, formally is like this weird set. But I don't think any mathematician uses this. So one of the consequences also of this is that in set theory, our primitive notions of let's say the basic mathematical structures or ideas which we use, they don't come in our theory. I mean, we can build them up from our theory, but it's not that they are like axiomized in our theory. For example, the natural numbers, we encode it like this. But also, for example, a function. A function is a subset of a power set of the product. I don't think that most of us use it like that. And then also another, I think, important part, and it's actually about proof checking. I mean, if you have like a long, complicated proof, a lot of people has to check it, and also a lot of time has to go inside of it. So ideally, what we should want is actually that we could like implement a proof into some kind of computer programming language or proof assistant, as it's called. And these are actually these disadvantages of set theory. We do not actually have this in type theory. Type theory is so that it is actually, in a sense, constructive. In more to say, like for example, these primitive notions, as we will see, our basic types or the type constructors between them, it's not that they will be constructed as some kind of weird set just to make it all work. They will be axiomized in our type theory, and also because of this formalization, we are also allowed to implement it inside of the computer. And it's also, I will give like a small demo also to see how this works. And it's not only that the computer just checks our proofs, but it will also really help us to create proofs. It can simplify, for example, goals, keep track of all things. And then also something else, and this might not be as important for everyone. But well, the thing is, in set theory, it's very important in, let's say, just ordinary one categories, or there is like let's say a big connection between the two. Just to give some very vague small idea, a set you can always consider it as like some discrete category. Well, some of us call it is like a zero groupoid. Well, types, they will no longer correspond with these discrete categories or zero groupoids, but they will correspond with infinity groupoids. And so type theory will give a more natural setting to study infinity categories. And also, well, conversely, I think the two, both type theory and the infinity category theory, have like a big interplay, and well, each of the subjects benefit by using the other. Okay, yeah, so now go a little bit more into the mathematics of type theory. So we're going to first start with actually saying, well, what is type theory? So in type theory, we have some basic types, and these are the basic building blocks. Type, well, we just denote them by capital letters. At the moment, well, just for a couple of seconds, you can think of a type as being some kind of set. It will also have elements. Now, in an element, well, we write, for example, instead of using like the membership relation, we use like a double colon, well, precisely to make the distinguish. Well, some authors in type theory really use the membership. Now, well, such elements, depending on how you look at types, we also call them points or terms. And one more thing that we have with type theory is definitional equality. Is for if you have like two elements, either they're zero by definition or not. They're equal by definition or not. So to give some examples, well, we have just empty type. It just has no elements at all. We can consider the type of natural numbers, whose elements are the natural numbers, in our how we think of them. But there is also a type of set who contains all the sets. So and here you already see like a little bit of a difference also between set theory. If you want to speak of like the set of sets, that's possible. You have to use some kind of meta theory. Here in type theory, we actually just hereditary forms the type from some. So everything in type theory is either a term or a type itself. We don't have to refer to something else. And then also there is a type of all types, or we call it the universe. Well, simply speaking, there is like a hierarchy of universes, but this detail we will omit in this talk. And so, well, are types just sets or some bigger count of sets? But no, definitely not. And the reason is because of the elements. In set theory, you have that being being a member of, it's a proposition. Either, well, you have that any element which it can be in a set or not. In particular, it can also be in multiple sets at the same time. But in type theory, we do not have this. This is a judgment. What I mean with this is if you have like every type has its particular terms, and so each term has this type. Well, it's related with this type. It can be in different kinds of types. And so actually, so it's I think not a good idea to think of a type as a set. But of course, this is how type theory started. But I think after a couple of years, they noticed that this is not the right way. So then, what are types, or how should we reason about it? There are.
So the points in terms, what does it refer to? So is
it is
a point and capital A a term, or what?
Yeah. So the big A it's a type, and then the small a it's a term. So it's like writing just A in A. It's like writing just something like this in set theory. But then, in order to make a distinction, I just use a colon.
The term is the capital A or the whole thing?
No, the term is actually just the small a.
They're similar, the same thing.
Elements, points, and terms are
Yeah, indeed. Yeah. Oh, yeah.
But they have no different name.
Yeah, indeed. Yeah. So my apologies. And a little bit unclear. Yeah, it's indeed either you say it's an element or a point or a term. It depends on how we look at types. So.
And should I think of this like as a language or so?
Yeah, indeed. Yeah, that's indeed actually the whole point of type theory, that this will be expressive enough to actually formulate a lot of mathematics side of it. So this is what I was going to say actually right now. One way to look up of type theory or types is by the very Howard correspondence, and that is where you think of a type as being a proposition. So, and then you say, okay, a proposition, it holds if our type is inhabited. So if it has terms or points or elements. So this is so one of the, to give some examples. I mean, if you have like two types, we will see that one can define like the type functions between types. And you always have that. Just if you go from the type of functions from A to A, it will always be inhabited just by some kind of identity function. And so in this says that if you think of these types of propositions, well then A implies A.
So the statement A implies A is a proposition, which in type theory would be called a type A implies A.
This is a type on its, this A implies A, it's a type on its own,
right?
But it's indeed constructed from the type A.
Right. Okay. So it's not, the arrow is not an extra part of the language of the type theory language.
Actually, we are going to add it.
Okay.
So the thing is, in type theory, so you have some, let's say, some basic types, and then you specify which kind of rules are added. It's a little bit like saying category theory, which limits or something like that. Yeah. This is all just for some to get a little bit of intuition or. And then there's also the other interpretation. This is the interpretation which is taken in the homotopy type theory. So, and there, types are spaces. So you think of a type as a space, and you do not have to think of a space like some topological space or something like that, but actually just a space in the sense of you have you have points of the space, you have elements, and we will also see that you can talk in a certain sense about homotopies, paths and homotopies between them. So the elements are points. So I think, for me, let's say officially I'm a computer scientist at the moment. So in the first one for me is a little bit more important, but I think that the second also has its own value, and I mostly come to focus especially at the end towards this homotopy interpretation. Okay. So now we're going to see how we could construct new types from old ones. Before I do that, first some notation. This is just which notation which logicians use. So the first one is like this horizontal bar, and it says on the top we have like, let's say, our hypothesis in a sense, and then on the bottom is something which we can prove. In this case, if you have like, abstractly, I'll just give the example. If you have like two natural numbers, if we can add them and we get again a natural number. And then also, and this is something very specific to dependent type theory, and that is actually if you have this notation, it means the following: if you have like a type together with the term, and then you can have like a dependent type in a sense that we associate a type to this X. We do this for every term in this type A, and then we can take like another term of that to give some example. If you take, for example, here we just take a natural number, we can consider type of R vector spaces of dimension n, or we can just then the zero vector. And so this is just notation, not important, just how this will become more clear in the rest of the talk. But as to say something about it. Okay.
So in the Curry Howard interpretation, you said types are the positions, and then the terms are the proofs.
Yeah.
Okay.
Indeed. Okay. So now I'm going to give specific constructions, or first in order to illustrate, I'm just first going to give actually a definition of the type of natural numbers. So if you work in type theory, this is something which you beforehand specifies that it exists. And in order to construct it, we always use like 4 different rules. The first is a type formation. This just says, this just creates our type. And in this case, we just have some abstract type of n. And we have the introduction rules. And the introduction rules, it just says how terms or elements can, how to say it, which kind of terms you have in this kind of type. And so in this case, you have always like the 0 element, and then for any natural number, we have a successor. And you see here already, the reason why I also started with this example is I think it is everyone here, or I assume that most of you know like piano arithmetic. This is precisely how it is done in piano arithmetic. It's not more like these fancy constructions and so on. They just specify how it should act, in a sense. And this is also how it's done in type theory. And so these introduction rules, you can very intuitively can think of actually, we have our type of natural numbers, how can we go into it? So kind of function in. We have also the elimination rule. It says how do we get something out of it. So how could we, let's say, construct a function out of the natural numbers? And this is actually precisely what the induction principle says for the natural numbers. If you want to specify a function, let's say in our case from n to c, well, how would you do this? Just by induction, you first say where 0 goes to, and so we then by c0, and then we have to say, okay, if we already know where n should go to, and so in our notation, I've written here then x, and then also it's mapped to y. Then we should also know something for its also means successor. And then if we just specify the data on this on 0 and on the successors, then we can conclude that it's also for all the natural numbers. As for the experts in the audience, this is actually this is a little bit restrictive in the sense that actually it's a little bit more than what I've written here, which is to keep it somewhat simple. And then lastly, there are also the computation rules. And the computation rules, they actually combine the introduction and the elimination rule. So in this case, for example, if you just would do this elimination rule, then you get like a function out of natural numbers. It depends here on this n, which you precisely get if you would just plot in n equals 0. Well, you would expect to precisely get C0 back. And this is precisely visible here. And then you also have for the successor. Yeah. So this is it might seem a little bit complicated, but it's just formally just saying how the induction principle should work. And so, okay, this was just some illustrative example. Now we come to the real constructors, so to say. So the first is the dependent function type. And this is written like this. So if you have a type A, and to each term we have some associated type, which I denote here by BA. Then we have the type of dependent functions. So intuitively, what should you think of it? You just assign to each to each term A you just assign something in a term in a B of A. This is how it should look like. Some introduction. Well, the introduction rule is actually quite simple. If you just assign to each A just some term inside of it, then you get a function. I've used the lambda notation, so you just saying that small a is mapped to B of A, but just to keep it a little bit concise. Then we have an elimination rule, which is, okay, you can just apply, if you have such a dependent function, you can just apply it to a term, and you get something B of A. And then lastly, there is a computation rule, which is, well, this is what you would expect for the application of the introduction function, which is given. Okay, so how does one think about this dependent function type? Well, if you would consider, so types are propositions. B of A is it is a type on its own. So you have like a term of this dependent product type, this dependent function type. Then what you can see, then you actually have that it, in a sense, interprets the formula for all A, B of A holds. Okay, and then concerning the homotopy interpretation, of course, you would think of it as some kind of function, but actually what is a little bit more interesting at the moment is this, let's say this big B. You can think of this as a function from our type A to our universe, or the type of types. And then actually this will be a vibration. So, and we will come back to this later, why this will precisely be. Yeah, well. So this is, and now there is of course the natural question: how could we interpret the existential quantifier, in a sense? And also, of course, if you have like this vibration, what would be the total space? And this is the dependent sum type. And so the dependent sum type is like the, let's say, the disjoint union. The disjoint union of types. Oh, sets. And again, and then its elements are then just pairs of an element, just in A and then also in B of A, satisfies the things which you would expect. You have some projection maps out of it, and then you should have some also combination of the introduction and computational.
Why do you introduce the lambda for the non-dependent type, the correct type, and then here you want to use just brackets, right?
Yeah. Yeah, indeed. Yeah. So that, yeah. Indeed.
Is there an intuition for why you will use
this notation?
Yes.
Yeah, because here you do not have functions, but here, I mean, if you just would consider, for example, B, that it's not dependent on A, so we just you have some fixed A and some fixed B, then actually what you precisely get is a product. So that's why you have a pair.
Okay, I think I'll look at it in a set way. I understand why it's there.
Yeah. Yeah, there's also, I understand, sometimes it can indeed be a little bit confusing. That's also why I spent quite some detailed time on this. Yeah. And so for the Wullaert correspondence, how to think of the dependent sum type? Well, if you just, again, it's like, if you get again think of B of A as some kind of proposition, then it means precisely that there exists such an A such that B of A holds, because if you think of a term in this dependent sum type as some kind of pair, and then just like the first function you get is A. And for the homotopy interpretation, you have that it's actually look like the total space within this vibration B. I think the more, let's say, this is the most complicated type constructor in type theory, and I think this is really the basic, the basis of type theory, and it's the identity type. And the identity type, okay, so what if you have like type A and you have like two elements inside your type, then we get a new type, which is called the identity type. I think it's like here, in this one way. Others will also call this like the paths type, the type of paths between A and B. This is already a little bit suggestion why homotopy theory comes into play. So one of the things is, if you I think it's more easily to think about it as the type of paths. So if you have like 2 points.
Maybe there's like it's X,
Yeah.
Y on top and then
Oh.
A, B.
Oh, indeed, yeah. That's a typo. Okay, my apologies. Yes, sorry. Yeah, I forgot to correct this. Yeah. Okay. Yeah. So if you think of this as some kind of well, this type should intuitively consist of the paths between the 2 points. And so if you have like just 1 point, I mean, you always have like an identity path between the two, or of course, in the query how the correspondence, x should always equal x. There's something which we would assume it will be inhabited or true. Then there is also an elimination rule, and this is the path induction rule. This seems quite, could seem quite complicated at first. But what it actually boils down to is if you want to define a function from an identity type to another type, and it always suffices, let's see, by this path induction to assume that your path, so in this case it is our P, that is precisely such an identity path or a reference. And yeah, this is just what it says that. So, I mean, one of the things like this identity type, like the even the type of natural numbers, the dependent sum, they with this elimination rule, they say something about how actually we can construct functions out of it. Actually, what is so special about these types is these are actually called inductive types. We don't have to specify these rules. Actually, you can consider them as some kind of these in a semantical way. They're actually in initial algebras for some functor. But it's just like these elimination rules. They just actually say how the functions should look like coming from this type to something else. So this way, this in a sense initial. Okay, maybe here it's already a good thing to give some example of a small demonstration into the what is called a proof assistant. Here I'm going to show you just a little bit about how one can program proofs or how one can check it. And so, firstly, what I'm going to show with you is actually if you have like a path from x to y, then you automatically have a path in the opposite direction. And so the things which you would expect, they definitely hold. And so this is this programming language is called Unimath, univalent mathematics. So yeah, you see already just the structure of this file. I mean, it really goes with the mathematical reasoning. And so first we have some lemma, which are called an inverse of path. It takes in a type, 2 elements, a path from x to y, and now we want to construct the other path. So how do we prove this? Well, if I would just run the proof, what you automatically see here in the bottom is, well, on the top, this was this horizontal line again. This is what we have. This is what we want to show. Now, what I said is, we can actually, by this path induction, we can always assume that our path should be like this identity path. And so this is precisely if you would do the induction, your goal automatically changes x equal x, and then okay, we can just apply the identity path. And so we have our action. And this is actually the proof of, well, in type theory, how one should prove something like that. So although it's really complicated, this identity path and this path induction, it's actually very simple. And so, for example, here also, if we use our previous inverse of path, here's some notation, if we just compose, if you would just compose it with your path, is also something which you can do. and you automatically get back the just the identity part. So and this is again the same. We can just assume here that our P is the identity, and then we can just apply it our identity part yet again. So this is already a small demonstration. I'll come back to this later, but I thought it might be a good idea so that you could see a little bit how this part interactions. It's actually not how it's really spelled out. It's actually, as I said, actually something like the identity type. You do not define in this way. It uses some kind of inductive types, but this goes a little bit further. Yeah. So this is precisely what we did in the proof assistant, and to do it formally, you would just this is just how you would do it formally. I don't think it's that interesting right now. Also, we can define what is an inverse. In particular, we also have the identity part. The inverse of the identity part is the identity part itself. We can also define the composition of parts. So this is the transitivity of equality, and in particular, the composition of the identity part, which is the identity part again. Can also show that if you compose the part with the identity part, then you just get your part back. Now here is something which is, I think, very crucial detail, and it is the following. I say you have this identity types, and these identity types, you have to, let's say, if you just have something like A equals B, and this is in a type A. Now here, where does this identity type live in? We take the identity type over an identity type. And so here, I think you already, for some of you maybe, when you see the process, you can take an identity type, and then between proofs, or between parts, you can take again an identity type. You can repeat this. Okay, yeah, some other lemmas which you all would expect. Okay, yeah, so I was a little bit too early. This was the little part of the demo which I already gave. My apologies. Okay. And now, okay, so I've given you the basic type constructors. Now we're coming to, I'm trying to explain how you really would use type theory. First of all, what do we need for a foundation in mathematics? We need some way to do logic. This is precisely what we have already done. I've given you how you would like the for all and the existential quantifier would be interpreted. You can then imply the implication as the function, the conjunction, or in other words, the product is like the special case of the dependent sum type. You can also define the sum type, but this is something which I did not do. Negation, you would think, let's say, from a logician point of view, negation, what would it mean? If you would want to show that not A would hold, assume you have like, what you want is you want to have some function from A to the empty type, because you have the contradiction, then you would, if you would apply a proof of A, you would get something in the empty type which is not possible. So, and because of the identity type, we also have equality. So this
two columns correspond to the left column and right column?
So the left column is how one would write things in logic, how one would usually do. And here on the right side, it is actually how, to which is corresponding type theory. So to give an example, here is dependent sum. This this corresponds with the an existential formula, because if you would, the term in here is like a couple of A and then something of B of A. And so this means precisely that B of A holds if you have such a term in here. Oh, yeah, my apology, I mixed up notation again. This X should be an A again. Maybe let me show you an example, which hopefully makes it a little bit more clear. consider the following type. What this says is the following. For all n, there exists a k of n such that n equal 2k or n equal 2k plus 1. This expresses the fact that, well, every natural number is either even or odd. But this is how you would write this down in type theory, because you would say that this proposition or this type it holds if it's inhabited. And so if you have a proof of this or a term of this type, and you have a proof of this statement. Somewhat more clear.
I'm a bit surprised because, I mean, except that some symbols are exchanged, I don't see so big a difference between the two sort of things. So it's just using a couple of different symbols.
Yeah, well.
And for
yeah. Okay. Yeah. Okay. I understand what you mean. Now, this, of course, a little bit. Indeed, somewhat of the how to say this? No, it's of course indeed we need in just logic or set theory, and then indeed in type theory they're both foundations, so they should be able to express somewhat the same. But there is already here a very big difference between the two. That in set theory or in logic, you just say that something is true, or you just give proof of this. While with type theory, a proof it corresponds to a term, and so we have like different terms correspond in a sense with different proofs. To give an example of this, and this is about this composition, which I didn't really explain. So even if you if you just want to in ordinary setting, and you would have that if x equals y and y equals z, then we should conclude that x equals z. Now, in order to construct this, there are actually 3 ways to prove such a thing. And what you can do is you can just say, okay, so we take a proof in here, a p, and a proof in here, a q. What you can do is you can just do induction on p, then you get. So with this, we can assume that just our y is x. This is the identity part. We also change here x. And then here, what we are left to show is that we have a function from here to here. This is just the identity. Now, but one of the things which in this case you have, if you would just, let's say, naively use this definition of this composition, is that you can only show, or by which we let's say definitionally holds, is that if you would do something like p dot then the identity on, or is it set? Sorry, in the other way around, that the identity composed with p is p. But what you do not have, or well, you can show it, but this holds by definition. What you do not have by definition is a converse, that you would have something like q dot the identity is equal to q. And the reason for this is how this induction principle actually works. Well, I don't know if this argument made it actually more confusing or maybe more clear, but yeah. So the thing is, indeed, it already, of course, any foundation of mathematics should indeed do the same thing. But so you would expect that you are able to express the same kind of things. But well, already by construction, this is just very different. In the sense, when we talk about our natural number, it is a type and it's no longer a set. And so on.
So what you have on the board is the type of witnesses. Any number is even or odd. It just so happens that this type is inhabited by exactly one element. There's just one witness to that fact. But consider the alternative fact that there is a prime number larger than 10. can turn this statement that there's a prime number larger than 10 also in a type. Will be then the type of witnesses that there's a prime number larger than 10. And this type will be inhabited by lots of inhabitants. For instance, by the pair consisting of the number 11, together with a witness that 11 is larger than 10 and that 11 is prime. But it will also be inhabited by the pair consisting of the number 13, together with a witness that 13 is larger than 10 and that 13 is prime. And the cool thing is that you no longer have two layers. In ordinary set theory and logic, you have the layer of logic, where you write down your statements, and then upon that, you have the sets about which you reason. In type theory, those two layers are identified into one. You just have one language named type theory. You can use it both to construct your objects, your favorite PAD field, also to construct the statements, and also to construct the proofs of your statements. Very nice.
Yeah, so these are, well, to give some example, all n equal 0. Well, this is a type which is not inhabited, so the same because you do not have a proof of such a thing. But you can also formulate other things like these subjective and so on. So these are just statements from logic. But you, as you just said, you can also encode mathematical structures. To give an example, a semi-group, so just have some kind of general set together with the multiplication, which is associative. In type theory, this is how you would, well, define such a thing. You can just a semi-group structure, so just the operation. So you have like the operation which you pick out. Then for all elements inside of it, you have like a proof that associativity holds. So here you already see you have like just a basic mathematical statement, but also a mathematical structure. And so, as I said, you have like the two layers of set theory and logic, they come together. And so, and then with something like that, you can like define the type of all semi-groups, and this should then consist of not just of a type or a set together with such a structure.
In the Homotopy type interpretation, and for that sentence of the semi-group structure, you would have a path between the two prioritizations. But okay, so that's not like an associative up to Homotopy.
Yes, that is precisely what it is actually.
It is.
Yes, indeed. You are indeed correct. The fact is, if you would indeed take different proofs actually of the associativity, then yeah, it's indeed you actually you indeed have that something should indeed hold up to homotopy precisely because you need to have some paths.
I think you only have like not only one homotopy higher. It's not a seed. It's not
no,
infinity.
You don't have it's not an infinity.
No, in this case, no, sorry.
Yeah,
No,
saying there's
yeah,
a
sorry.
system of multipliers that says which one.
Yeah, in this case, it's indeed, yeah.
For instance, if you have three variables of pi, x, y, z, a, b.
Then you have like all your multiplies. Yeah.
These are not required to be equal.
Okay.
Yeah, and that is actually also, let's say, which is somewhat, let's say, the tricky part of type theory is that because of this these frequencies, these homotopies, you need to have this coherence. You also have these coherence problems, which you also have with higher categories or with these homotopies.
Yes. An explicit. Explicit one should be then an element of this type.
Yeah, the thing is you don't need you don't have like a natural choice in the sense you have like multiple choices, and this is from the moment on you would consider like multiple things. You have like multiple choices to just as you have like with the composition. Okay, So now a little bit more on homotopy type theory. So well, recall we have these properties, and well, if you think about it, it actually gives every type the structure of a groupoid, where then the interpart is then the homoset. But well, as I already said, we actually with these are higher groupoids, or infinity groupoids, because well, we can always take the identity paths between path itself, and we can keep going. And well, of course, these properties or some of these expresses that we actually have all the properties in order for the foreign category. So okay, now we are well, a big or something important in homotopy type theory are what's called the homotopy levels. And well, this is before saying a little bit more about it. Well, if we would just consider the following, if we have like the left statement on the top, exists an A such that for all y x equal y. This means precisely that our space is contractible, homotopy view. Now, if you would apply this to saying that for all x and y, this holds for the identity type, and this means that your type is a proposition. And the reason is because, well, you have like there is up to homotopy, there exists always a unique proof of the equality. And so if A is contractible, it actually is in some sense equivalent to a type with only 1 point. If something is a proposition that is either equivalent to a type with 1 point or with 0 points. And we can also apply this proposition to the identity type again. And you actually have that A is a set, or it's a 0 groupoid, because you just said that, well, you just have different kind of different endpoints, yeah.
So I think that this question that I'm doing now is related to the previous. But for example, so at first glance, it would seem that that first type that you have, actually A is connected. So how would you say A is connected? Because constructible, you need to have like paths and then like homotopies between the paths and so on. And there it seems like that we're just saying there is a path between X and Y. We're not giving like the coherence or something.
So you mean that if something is contractible, it's also a proposition. You mean something like actually this kind of thing that if you have like we know that every term are equal, and then if you have like then all the proofs should also be equal. Is that what you mean? Or?
No. So yeah, how would you say A is connected? Is there an easy way to say that in type theory?
Is connected. I'm actually not.
Maybe the question is, if I would read the left part of A is contractible, it says there exists an element, a point in our space A. But for every other point in our space A, there is a path from Y to X.
But the little part of that.
That's the more part.
Yeah,
That's what we're confused
Those
about.
paths given to you from X to Y need to depend continuously on the Y.
That makes it
and that makes it the condition for contractibility. And if you want the connectedness condition, then you need to have some center point X, so that it just will happen for any other point Y, there's a path from X to Y, but you do not require that these paths depend continuously on the endpoint. And the way how you put that in type theory is by using the proposition truncation. So the definition for connectedness would be the sigma, then the proposition truncation, and then the pi, and then the string.
Okay, well, this is continuing. No, second question. If you say A is a proposition, means that you have a contractible space of proofs for A, I guess. Do you then force on Booleanness? Because you only say something is a proposition, it's contractible, or it doesn't say anything about the validity of the proposition. position. Or it says when something is position. Okay. Right.
So for instance, the empty type is a proposition.
Right.
And also the type that 2 plus 2 equals, the type of witnesses that 2 plus 2 equals 4 is also a proposition. But the type of witnesses that there's a prime number larger than 10 is not a proposition.
Because you got this.
Because I have lots of inhabitants which are all distinct from each other.
What we said here is this is actually, if you, I mean, we have this very Howard correspondence, but actually if one, well, in homotopy type theory, we do not work with just every type being a proposition. And then we really, if we have like such a statement, doesn't matter what, then as I said, take like a propositional truncation, and is in a sense some universal proposition which lies over it. And then if you want to say really a statement inside of homotopy type theory, then you always consider this truncation. And this is also a little bit something which you even also do with, let's say, the internal logic of categories. Maybe to give some example, you can express just the axiom of choice inside of type theory as in the previous reasoning. Now, because this is something which you can prove inside of type theory. But because you can construct two witnesses of every. Now, what doesn't hold in general is if you take this propositional truncation, then it's no longer necessarily felt. So from the moment on, you actually really consider this actually, well, I think so I say this identified in the sense of complicated or made homotopy type theories. From the moment you allow that not every that the identity types, let's say, do not stop in a sense, you really get this, let's say, a little bit weird phenomenon in a sense. So with this truncation, you make it stop in a certain sense.
So choice is inhabited, but the propositional truncation of choice is not. That's what you said?
Yes, I thought so. No?
Okay.
I think so.
Almost. So if a type is inhabited, then so is its propositional truncation, because you have a map from the type to its proposition. But the propositional truncation signs are a little bit more to the right in the statement of the axiom of choice. It's hard to say it without writing it.
Yeah. Okay, that's good. Okay. I'm done.
What else was I going to say about this? Well, and then still one of the things which I was thinking of showing inside of the demo is if you have, like, for example, if you have some is contractible, then it also should be a proposition. It's a set, so that this is something which you would expect. And so let me open this proof assistant again. So why am I showing you this? I just find it really, I think, it's very amazing that we can implement something like that. And so, and we actually do just the same as one would do on paper. We define what is contractible. This is precisely the definition here. And then also a proposition. And then how would you show that contractible implies the proposition? Well, we have to show that something is, we have to find such a function. So we first take some term in here. And so a proof of being contractible. Yeah, we can even with such a proof assistant, we can involve definitions which we have. And so if you don't know well what if you want to show, I mean, it's like very complicated, you can just try it out. Now you see, okay, we just need to have two terms and we have to show that the identity part is contractible. And then, well, here we can then actually, since our type is contractible, we can just as well, in a contractible type, it has a center point. So if you want to show like x equal y, but we already have such a contractible center. We can just consider the parts to it, and then one of them take the inverse, you decompose them. So this is what I've written here. Sometimes it can be a little bit complicated to write out properly, but this is something I think this also has benefits. So, and here is again, I mean, this is again where this induction principle is very, I think, neat, so to say, and because we have to show it for any part, we can just use the identity part, and then what then you have is precisely just because this x equal y now, you have that these two parts are actually the same by definition. So because they are precisely chosen, and so we just have that we just take the inverse of each other, and so this is this is done, and then so of course the QED, the end proof, and also here this this H levels which I just saw, so something like contractible is a proposition and so on. Is a set. Well, we always define them recursively in what we have defined before. And so there is some induction definition. This is also something which you can easily write out like this. And if you do this, then you can really show that these levels go, let's say, upward. Then we can just do like an induction on this n, and then everything all products out. I think you get the point how it is somewhat done. I mean, we can, of course, we need to have like a base case. We already proved this, so we could just use our previous lemma. And yeah, you see here the proof is complete. So it tells you when you are done and not. And then it's just the same. Well, first, we should hold for all A. So we just take an A and then take a proof of here. And we have to show something of an A level, so we have to show something for different kind of terms. Then we can just apply the induction hypothesis. So because of this induction, this unimod automatically gives us some the induction hypothesis, so that we don't have to write it out, and then it's just a function, so we can just apply it to, in this case, A equals this identity type. So this is how one works with a proof assistant. This is sometimes it's because of all the different witnesses, it can make it a little bit complicated, because this homotopy you have to sometimes like transport along paths, which let's say in general in a set level or one categorical sense you do not have to do, but again quite a lot is already implemented in here, and so you can really you can search for lemmas very easily. And so on. So in this setting, such a proof assistant really helps you also to write proofs, and then again to check, because you have to keep track of so many things at once. It's really good to so because this Unimod is actually a library, and there are I think quite a lot of things already implemented. At the moment, I'm implementing some things on monoidal categories. By categories are already implemented on other categories. Things like quadratic forms are not implemented. My apologies for some of you, but I mean, a lot of those things are already. So, and I think this was the end of my talk. Anything else to say? Oh, yes, of course, a little bit more on the homotopy, but well, then.
You can have a few minutes.
Okay, yeah. Okay, so, things you automatically get for free in type theory, like this composition of paths and so on, without too much work, is, you can show that any function is continuous in the sense of path continuous, in the sense that that if you have a path from x to y and you have some function, we can just we automatically get a path in the image. So in the sense it's path continuous, it preserves the identity, and this is Then one shows it just by induction. And by induction, one assumes that our path is the identity path, x equal x. And so fx equal fx, just take the identity path. And we can also show other things that is, let's say, tutorial in any possible way you might imagine, in a sense. And then, well, as I said in the beginning, a type family, you think of it as some kind of vibration, a little bit more formally why. Well, if you path, then you automatically get, well, a function like this, again probably by induction. And then, well, why is it, let's say, a vibration in a sense, is that if we choose such a point in like this, in this type of x, then and then for any proof we can actually always lift this s, so they have like the same like the same beginning in every point.
I'm just trying to unpack all the definitions, I guess. So the thing is that you just cannot work with vibration, I guess, because if you define this type families are automatically vibration. Same as you always work with continuous functions, because you cannot see that. So you have to pour something in between us.
Yeah. So that's what is so powerful about it in the sense that it automatically already, well, as you say, it's in a sense somewhat restrictive, but in a sense you automatically get so much things for free, which makes it like an unnatural setting to do certain things.
Yeah. I think to some extent it's funny if you propose it as a new foundation for mathematics, where you state that functions being seen as subsets of products are indirect, and making proofs and everything types is in some way also an indirectness of making your whole reasoning one thing.
So you lost me.
Well, that's, so Ibrahim states in the set theoretic foundation of mathematics. I really like types, but from that explanation where you say, okay, we start from sets and we build everything in form of sets, and the idea from types is that you can also work with some undefined functions as sort of sets of some subset of product, but define them as their own entities, as primitive notions. But it feels to me like using type theory even goes farther because it wants to make everything a type. Yep. It makes proofs indirect as types instead of making it as separate entities as primitive notions. So in some sense, in type theory, there is even less primitive notions. Everything is a type. But I'm not opposed to that. If you want to make the point that it is primitive, it's not at all primitive.
That's a great unifying advantage of that.
Right, and that's, I guess, maybe if I can have a question on this. So the next step I would then see is like, they always say proof assistants need type theory to make something verifiable. What do you think is what is the main or the significant difference between these different foundations of mathematics which makes it checkable? Is it because any element can only be of one type instead of being in multiple sets? Why does it work with proof assistants?
Well, I think how I consider this is actually precisely because we do not have like this specific implementations of everything. There are like set theory based proof assistants, but yeah, I think so like now all proof systems are in type theory.
I know.
It says enough precisely because we have like this difficulty of how to in a sense, represent things, while with this type. Well, the thing is, such a proof system is always based on functional programming languages. And in programming languages, you already have like this notion of, well, everything there is based on types, or like, well, tightly functional programming languages, at least. But it's just you already have it like in there, and if you would make like such a proof assistant, then you just, in a sense, give like, say, you put on some axioms or like some functions in the sense of how axioms should work. In a sense. You add some kind of you just add functions in a sense to your library, which automatically works.
I think theoretically, proof assistants based on set theory would work just as well.
Yeah, that's what I guess.
But set theory is not made for humans. Set theory is made for being absolutely minimalistic. The part of you're pushing that idea of minimalism to the very end. And it just so happens that type theories, proof assistants with type theory are made for human consumption. You can actually program it, and it's a joyful experience. I know I know very few activities which are more fun than programming mathematics in the computer. But that's only unlocked by type theory.
Right, but do you think that the foundational notion why this works human-based is that everything is a type? That is because it's verifiable types?
I think there are like 20 reasons why type theory is a better foundation from that point of view than set theory. One is perhaps that an ordinary mathematician who has not received any training in logic already is a type theorist without realizing it. Because we are thinking in types. We're thinking like the type of real numbers, the type of complex numbers. And for instance, you would never ask a mathematician whether the reals are an element of the number 7. Never ask the question because it's ill-typed.
Right.
But in set theory, you may ask whether the reals are an element of the number 7. And the answer will depend on the precise definition of the number 7 and the reals, and it will not be preserved under isomorphism of fields.
Right, but don't you also want to say in mathematics if 7 is an element of the reals or the natural numbers?
Sometimes you do it, but most of the time, when I'm talking about a number, I already had attached to it a set of numbers in which it is included.
Right, but if you took for the number 7 as of the type natural number is different from the number 7 as a type real, which is some sort of a different perspective.
It's a little bit of a different perspective, but it's not a big issue. You just have to cast the natural number 7 into the real number 7, just one function call.
Right.
And I think it's good for mental hygiene to distribute mental hygiene, like for soap.
Yeah, I get it.
I learned that term from Andy Bauer. That is distinction between the natural number 7 and the real number 7. They are distinct entities.
Right. Okay, no. Yeah.
We're already going on a little bit longer than expected. So I would suggest to end here, at least
I was finished.
formally.